Okay, so in this video, I would like to prove that the integral of the complex function 1 over z is equal to pi times I. So I want to prove that this is equal to pi times I, where we integrate around this semicircular curve here. So you want to imagine that this curve is basically 1/2 of the unit circle. So there's kind of a missing half over here. And we want to prove that if you integrate 1 over z just around this half of the circle, then you'll get a result of pi times I. And this is basically 1/2 of the proof of a very important theorem in complex variables, which is that if you integrate 1 over z around this entire circle, um, regardless of where you start, the result is 2 pi I. And that's a very important result in complex variables. So here we're just working with this semicircle. And an easy way to do this integral is to use the fact that, so 1 over z is a complex valued function. And on certain domains, 1 over z has an antiderivative, specifically log z. Okay, so if we pick a branch of the complex logarithm, its derivative everywhere away from the branch cut is going to be 1 over z. So for example, if we choose the principal branch of the logarithm, and that's what I'm writing here, it's capitalized, so it's the principal branch. So that has a branch cut over here on the negative real axis. So this is your branch cut. This is where log z is going to fail to be analytic and also fails to be continuous. But anywhere away from this branch cut, so like on the semicircular curve that we're dealing with, log z is perfectly analytic and well behaved and everything else. And if you take the derivative of log z anywhere away from this branch cut, you just get 1 over z. So there's a theorem which is similar to the fundamental theorem of calculus, which is that when you integrate over a curve like this, so if I integrate over this semicircular curve and I'm integrating 1 over z, well, I can do that integral by just finding the log at this point right here where the curve ends, and then subtracting the log at this point over here, right? So if I want to do this integral up here, what I can do is I can take the antiderivative, and the antiderivative varies depending on the function you start with, of course, but in this case it's log. And I'm going to do log of I, okay, minus log of negative I. Okay, because I'm starting the curve at this point down here, which is negative I, which is on the unit circle, and I'm going up to this point here, which is I. So whatever this integral is, it should just equal log of I minus log of negative I. Okay, so the only thing that's left to do is we need to find log of I. We can recall that, if we want to find the logarithm of a point that's on the unit circle somewhere, the logarithm of that is just going to be the argument of the point. And in this case, it's going to be the principal argument because we're using the principal branch of the log. So what does that mean? Well, I can write log of I as pi over 2 times I, okay, because that's the argument of the number I. And then if I want the log of negative I, that's going to be negative pi over 2 times I. And then I'm subtracting. So overall, if I simplify this, I'm just going to get pi over 2 times I plus pi over 2 times I. And that's going to give me my result that I already wrote, but I'll write it one more time, that this integral is equal to pi I. And if you want to prove that the entire integral is 2 pi I, you would want to choose a different branch of the logarithm, and you would want to use that to compute the second half of the integral, and then the result would just be the two halves of the integral added together. And that's it.